One of the things that I often think of as an application of calculus in biology is that calculus gets used pretty often to measure the growth of populations. And the simplest example of how to model the growth of a population, so say I have a bunch of bacteria in a petri dish, or maybe a herd of deer out in some forest preserve somewhere, something that's kind of reasonably a closed system. One of the things that we might say is if we let y be the growth rate of the population, maybe this is in organisms per year, and x is the actual population in a given year, we can find relationships between x and y, the simplest of which is often called the Malthusian Model for population growth. I've never heard that before in biology, population modeling, Malthusian growth. And okay, if you've heard it, the passing familiarity is more than enough for what we'll do today. But the idea behind that simplest possible model is that it's just linear. Y equals kx. This is the Malthusian model. And under this model, if my population of organisms has 0 organisms in it, what's the growth rate going to be? 0, right. If I don't have any organisms in my dish, I'm not going to get any growth rate. Right? I'm never going to get anywhere until I at least have some organisms. So let's say I put 1,000 bacteria into my dish or something like that. Now my growth rate is going to be some positive value in organisms per year. And so my population is going to start growing. Well, what's going to happen to the growth rate as my population starts growing?
Speed up?
Yes. So larger populations are going to speed up the growth rate. Speeds up the growth rate. And it turns out that this is a pretty decent model for population growth if I just have maybe a small number of organisms in a really large environment where they have all the resources that they need to grow and they can just grow like wildfire. Because it turns out that if we take the equation, the Malthusian population growth equation, this might be something you can do later this semester, and determine how the population would actually grow over time in this model, it would be exponential growth. Every year we would have the same percentage more population organisms as compared to the year before. So maybe 10% per year or 100% per year or something. And it would just keep taking off in an exponential growth situation. Which again, if the population has all the resources it needs to eat and to reproduce and do all that stuff, this is a pretty decent model. But it's not a very realistic model once the resources start to become limited and they start to run out. That we would expect in a small petri dish, eventually, organisms start bumping into one another, competing, little bacteria elbowing one another out for the resources in the gel, right? And so probably this is not a very good model as populations get larger or as resources get more scarce. So we can go to a model that maybe looks more like this for population growth. This would be a model we call the Logistic Model. Again, y is the growth rate in organisms per year. X is the size of the population. And again, this has the property that if I have no organisms at all in my colony, then I'm not going to get any growth. And we might say, if we take this small little area down here where we don't have very many organisms and we sort of zoom in on it, if I zoom in on that place far enough, if I take a really magnifying glass to it, it looks like a straight line again, right? So for very small populations, this looks just like the Malthusian model did. It's just a straight line. But when the sizes of the population get bigger and the resources start to run out, we see a different effect. That in fact, eventually there comes a point where if my population gets big enough, there are so few resources left that they're competing for that their growth rate goes back down to 0 again. That's what happens in a logistic model. Logistic growth. Rather than y equals kx, as it was in the last example. In the logistic model, it looks like y equals, let's write it as kx minus ax squared. So we make the model a little bit more complicated for the sake of capturing this behavior of what happens when overpopulation starts to take over. Right? And in fact, we might even be able to continue using this model if we had more than 4,000 organisms or whatever, and end up seeing a population that begins to shrink instead of to grow, getting a negative growth rate. So these are two kind of as simple as possible, but still they try to capture some of the behavior that we would need to capture to model the growth of populations in two different ways. The Malthusian model, where that growth curve is just a straight line, and the logistic model, where it's one of these kinds of functions. And what do we call these kinds of functions? Quadratic. What is it that makes this a quadratic function? What part of the formula are you looking at? Yeah. So having an x squared, so squaring our independent variable, that is what makes this kind of function quadratic. What is it about the graph that indicates that this is a quadratic function? What do we call this kind of graph? A parabola. So the parabolic shape of the graph is a giveaway. Okay. Great. So for that kind of function, and by the way, every quadratic function has a formula that looks like what? F of x equals. So this is one kind of example. So I have an x squared. I've got an x, but then I can also just have a constant, right? And so we could take this as an opportunity real quickly to just play around with those parameters a little bit. So y equals ax squared plus bx plus c. So what happens when I play with the value of a, the one that's in front of the x squared? What do you think changes when I change that? Call it the leading coefficient.
It's stretching or...
Right. So putting our pre-calculus hats on, one of the things we can think of is, since that thing is multiplying x squared, it's having an effect of either a vertical or a horizontal stretch. So if I make a very large, if I make a from 1 up to 5, let's say, what's happening to my parabola? It's getting narrower because I'm applying a vertical stretch to it. If I make it smaller, like 0.1 or something, now that's applying a vertical compression to it, so it's getting not as steep. So that leading coefficient, what happens when I make a negative? The parabola flips over, right. So that's another piece of intuition that we can have about parabolas. It's also later on going to tell us something about all kinds of functions, is that when a is greater than 0, the parabola points up. So it has the U shape. When a is less than 0, it points down. Later in the semester, we might as well introduce this vocab word today. We will call these two situations concave up, when the parabola opens upwards, and concave down when the parabola opens downwards. And it's real easy to tell for a quadratic function when these happen. We just look at the leading coefficient, the coefficient in front of the x squared. But we'll be able to say these same kinds of things about other kinds of functions as well later on in the semester. And by we, I mean all of you and my wife, right? And me if you come visit me in math services across the street. But so that leading coefficient controls the concavity of the function, up versus down. Which way does the parabola go? So that's for A. Let me leave B for a minute and let's talk about C. What's going to happen if I change the value of C? Yeah, just like with our linear equations, that C, that extra constant, is just a vertical shift. So if I increase it, it's going to move my whole graph upwards. If I decrease it, it's going to move my whole graph downwards. But that's about it. It doesn't change the shape of what the graph looks like. That seems to be controlled mostly by A and B. B is a tricky one. So let's just change it and kind of see if we can describe what's happening. If I take B and I, say, stretch it from 1 up to 4, or bring it back down to, instead of 1, let's say I do 0. So there's some real interesting kind of a mixture of different kinds of behavior as I change this value for c. It's not at all clear how to describe that in one sentence. The way to think about what b is doing for us is it's changing where this parabola's lowest point is. What do we call the lowest point on a parabola? It's got a name.
Vertex.
Vertex. So for this particular example, I've set b equal to -1, and there's a vertex on this parabola. What is the vertex, just looking at the coordinates on this coordinate system here? What does it look like?
1.
The x value is 1, and the y value, it looks like these are counting by maybe 1/2 in the y direction. So I would say that the y value looks like 1/2 to me. 0.5 if you like decimals. Okay, so b somehow is controlling the vertex, the location of the vertex. So let's pause for a moment and talk about vertex. The parabola that we're looking at has the equation y equals 1/2 x squared minus x plus 1. So who remembers what nifty trick that we can use? There are a couple different options to discover the coordinates of the vertex for a parabola that's written in this form. Anyone have any shortcuts or formulas you remember or techniques? So that's my favorite shortcut for a parabola written in this form. I think it's also your professor's favorite shortcut for it, is that you can find the x-coordinate of the vertex. Sometimes it's called h in some textbooks. I don't know why they use h. But as minus b over 2a. By the way, what do a and b stand for in this example? Yeah, it's the coefficients, respectively, of the x squared term and the linear term, the x term. So in our example, a is 1/2. What is b? For the formula written in purple up there, what's the value for b? -1, yeah. And so if I evaluate minus b over 2a for this parabola, I'm going to get upstairs 1, downstairs 2 times 1/2 is 1. 1 divided by 1 gives me 1. And that's what we saw on the vertex of this parabola on the graph. Then how do we find the y-coordinate of that vertex? Sometimes called k.
You plug it in.
Plug it what?
Plug the 1 into the 1.
Yeah, the x value that we found for the vertex, plug that in. What are we plugging it into?
The function.
Right, the equation that defines our function, f of x. So it's just f of h. So we'll just do 1/2 times 1 squared minus 1 plus 1. Just plugging a 1 in for x into our formula. And sure enough, we evaluate all of that out, and we get 1/2. So finding the vertex of a parabola tells us, in this parabola, it tells us its lowest point. Will the vertex always tell us the lowest point of a parabola? When does it not? Right. When it doesn't tell you the lowest point, it's telling you, instead, the highest point. So if we go back to a value of a, so what do I have to do to make my parabola point down instead of up?
A needs to be negative.
Yeah, just make a negative. And so now, the vertex of my parabola is no longer the lowest point, but it would be the highest point. The good news is the formula still works, right? We can still use minus b over 2a to find the x value, and then plug that x value back into the equation to find the y. Okay, so now the last thing I want to do with this, and I'm going to see if I can make this not too obnoxious. The last thing I want to do with this is talk about intercepts, just like we did with the linear functions we did a little while ago. Beginning with the y-intercept. How do I find, again, we know there's only one y-intercept. How do we find it? Yeah, set x equal to 0 and use the equation, which I have to write the equation of this parabola. Here a was -2, so this is -2x squared plus 1x minus 1. And so if I set x equal to 0 in that equation, I'll find y equals -2 times 0 squared plus 0 minus 1, and now something's fishy. Yep, I have a typo. My apologies, it's plus 1 in the equation. And so what is the y-intercept? y is equal to 1. The coordinates are just 0, 1. So there's my y-intercept. Okay, so that wasn't so bad, and there's only ever going to be one x-intercept. Okay, what about the y-intercepts? Sorry, what about the x-intercepts? Yes. So we'll set y equal to 0, and then determine what x should be. And so this is probably going to take a little bit of doing. If I put a 0 in here for y, now I have an equation that I need to solve for x. And that's not the easiest thing in the world to do. It's not the most obvious thing in the world to do. But you have some tools for it. What are your ideas? How could we try to solve that equation for x? Factoring would be a great choice in this equation because one side of my equation is already 0, which anytime you're thinking about factoring to solve an equation, make sure that one side of the equation is 0 before you do so. And since that's true, factoring would be a good choice here. Can anyone see how to factor this quadratic expression on the right-hand side? I think it factors nicely, but it's not immediately clear how to do it. Well, first of all, the first thing I would do is I would multiply both sides by -1, just to get the negative off of my leading coefficient. So this will be a minus, and that'll be a minus. That might make our lives a little bit easier. But then to actually accomplish this factoring, here's the trick I like. And you don't have to use this if you don't want to, but I teach our Math 95 here at Bridgewater a lot, and I share this. I learned this by teaching Math 95. So how I want to do this is take the 2x squared and ask what can I break 2x squared apart into to factor it, just to factor that part of it. A 2x and an x. We know that no matter what we do with this, our 2x squared is going to have to come from a 2x times an x. But then, once I've done that, what are my two possibilities for how to multiply two numbers and get -1? Right, there's really only one possibility, but you sort of flip-flop them into the two different areas. It has to be a +1 times a -1, if this is going to factor over the integers at all. So we could try -1 here, +1 here. Or we could try +1 up there and -1 down here. I'm going to save us the step and just go straight to this one, which I believe works. And we'll know that it works just by multiplying everything else here back out. 2x times -1 in the upper right gives me a -2x. X times +1 in the lower left gives me a +x. And sure enough, when I add together the like terms in this cell and in that cell, I'll get -1x, which is what I wanted for my middle term. So factoring is definitely an option when you can see how to do it. In this example, it gives me the factorization 2x plus 1 times x minus 1. And then what do I do with that now that it's factored? If I FOIL, I'm just going to go right back to where I started. So solve what, though? Yeah, right. So what I get to do is I get to split apart these two factors so that each one of them has their own simple equation to solve. 2x plus 1 equals 0, and x minus 1 equals 0. The latter equation gives me x equals 1, and sure enough, that seems to be one of my x-intercepts. And the former, subtracting 1 from both sides and then dividing by 2, gives me -1/2. So I ended up with two x-intercepts this time. And by factoring, I found out what the values of those were. If I didn't want to factor, what would be my recourse? Yeah. And I have to say, I think this is probably the recourse that your professor prefers. Because the quadratic equation always works. Factoring doesn't always work. So we can use the quadratic formula instead. Who's got this off the top of their head today? Yes, great. Gold star. There's the quadratic formula, for which all we would have to do is substitute what for A? And B? 1. I think actually didn't I screw this up? I think this is a minus. and c is minus 1. Yeah, no, the rest of our work was fine. It just when I copied that line, it didn't get negativized. So right, we would just plug that in and we would do the simplification and the plus and minus. What do you do with this plus and minus? Right, so you end up with two solutions because you do the plus one time and you do the minus the other time. And that will give us the same set of answers also.